Hello, we are going to continue in Unit 8 with Topic 2 on pH and pOH of strong acids and bases. So we're going to take a look at how we determine what the hydrogen and hydroxide ion concentrations are and then how we calculate their pH from there. First, let's talk about our strong acids and bases. So the 6 strong acids and 12 strong bases listed below and that you memorized are considered strong because they completely dissociate when placed in water, creating a large Ka or Kb value as the reaction favors the products. Some of them have Kas and Kbs so large that they really can't even be measured. So our strong acids we have listed hydrochloric, hydrobromic, hydroiodic, then nitric acid, sulfuric acid, and perchloric acid. So those are the 6. We have them memorized. If they're not on that list, then they are weak. Same with our strong bases. We have them all listed there, but they are the group 1 and group 2 metal hydroxides. If it's in group 1, then we add 1 hydroxide. If it's in group 2, we add 2 to balance the charge. So let's take a look at the dissociation reactions for the acid, for one acid and one of the bases. So these are the commonly used one, hydrochloric and sodium hydroxide. So if we look at the our first acid here, hydrochloric acid, when it's aqueous, dissolves into or breaks down into hydrogen and chlorine. Now, if we look at the Ka value, it is 1 times 10 to the 7th power. Most of our Ka values are have powers that are negative, right? They're less than 1. This is very large, right? Much greater than 1. So it is greater than 1. Which means we're going to mostly have products, right? We're going to shift our reaction mostly to the products. Our pH here is negative 3.5. Okay, so we talk about the pH scale being from 0 to 14. That's kind of true, but not really. Our strong acids, things like hydrochloric with their Ka values, they can have very small pHs. They can even have negative pHs. We don't see it a whole lot in this class, but it's good to be aware that that is possible. So it is super acidic. Our sodium hydroxide, the next one, when aqueous, separates into sodium and chlorine ion. Oh my gosh, not chlorine, hydroxide ion. I don't know how I got chlorine in there. All right, OH minus. So our Kb value is 6.3 times 10 to the negative 1. If we found our pH from that, it would be 13.9. So right almost at 14, very, very basic. So these reactions, you'll notice I've put just the one-sided arrow. Almost no reactant exists here. So we basically assume that the concentration of our products, our hydrogen, chlorine, sodium hydroxide, all of those can be found from the concentrations of the whole solution. So this only applies to our strong acids and bases. We can find the concentration of our products from the concentration given of the solution because it's basically all product. So that's a little shortcut for us. Not really shortcut, but something to be aware of. So let's just compare our strong versus weak acids and bases just so we know where our difference is. So in this PowerPoint, in this set of notes, we're really focusing on the strong acids and bases. Those are the ones on our list that we memorized. If it's weak, it's not on the list. Okay, so that's why we memorize only that handful of acids and bases because every other one that we encounter is going to be weak. Most of the time, our strong acids and bases, when we see their dissociation, we use the single arrow. Since it all breaks apart and forms our products, mostly we get very little equilibrium happening there, so we assume that it's all product. When we look at our weak acids and bases, we use that double arrow for our dissociations since it creates an equilibrium and doesn't all break apart. Our strong acids and bases are going to have a large equilibrium constant, large K value. Weak acid and base would have a small K value. Remember, these are going to be, when we say large K value, they might be 10 to the just like negative 1. They might be 10 to a positive exponent. Small K values are going to be like 10 to the negative 4, 10 to the negative 12, 10 to the negative 16, things like that. So those are much smaller values. Remember that that 10 to the negative value is moving your decimal to the left and giving you more and more zeros before you get to your actual number. Okay, so much smaller decimals. To find our hydrogen or hydroxide ion concentration, we can get it from the molarity of our acid or base. If we want to do it for weak, we have to use an ice table at equilibrium. Okay, so we're going to be getting to that in topic 3. We got to establish our equilibrium and go through all of those steps like we did in last unit. But if it's strong, we have an easier way of finding the concentration. So let's look at our pH of our strong acids. Just focus on our acids for now. So we can write dissociation reactions by separating the ions for any of these strong acids. And there's only 6 of them, remember, so this is the same basic process over and over again. So we've got our HCl forms H plus and Cl minus, pretty straightforward. If you have something with more than one hydrogen in the front, like our H2SO4, that's called a, we have a couple words. We have diprotic. Remember that proton idea is a hydrogen ion, so diprotic means it has 2 hydrogen ions. We can also call it a polyprotic acid. Poly meaning many. So diprotic, polyprotic, those are acids with more than one hydrogen. A monoprotic acid would be just 1 hydrogen. So this is a polyprotic acid or a diprotic acid, H2SO4. When we break it apart, it's only losing 1 hydrogen at a time. Okay, it doesn't react both of them. So that does simplify things. We're still keeping that 1-to-1 ratio, and the other hydrogen just stays with our SO4. And since we only lost an H plus, then the HSO4 is just negative. So 1 plus, 1 minus. Now, we can also write these showing the water molecule. Remember that when acids react, they give up hydrogen, and it's in aqueous solution. So the water is there. So you might also see it written like this, where it's HCl, and it forms the hydronium ion and then the chlorine. So hydronium, remember, is water plus a hydrogen ion. So that is another way of writing it. It's interchangeable. These two could be used interchangeably. Even if we were doing some sort of equilibrium type thing, your liquid water crosses out and it doesn't matter anyway. So it makes things easy. So since all of them have a 1-to-1 ratio of the solution on the left and the hydrogen on the right, the concentration of our solution is equal to our concentration of our hydrogen. They're interchangeable. So for example, if we have a 0.7 molar HCl solution, well, what's the pH? Well, if our concentration of HCl is 0.7, that's equal to our concentration of hydrogen, because they are, we can see up here, a 1-to-1 ratio. So our hydrogen is also 0.7 molar. If we then want to find our pH, we would do the negative log of our hydrogen ion, or negative log of 0.7, and we would get 0.15 for our pH. That is a very low pH, very low, so this is super acidic. Okay, so pH can also help us determine how, based on our molarity, what the acidity of our solution is. So if we change the molarity, that does change our pH, just because an acid at a certain concentration has a certain pH doesn't mean it always has that pH. We can dilute it and it's going to change the pH of the solution. So that's something else to be aware of. So pH is controlled by the strength of the acid, basically its Ka value, and its concentration. It's not just one or the other. So let's take a look at another example here. It says, what is the pH of a 0.9 molar solution of HBr? So if we think about HBr, breaking down, we'd have hydrogen ion and bromine ion, bromide. So if this solution is 0.090 molar, then it's a 1-to-1 ratio with our hydrogen and our bromine. So if we want the pH, we would do the negative log of our concentration of hydrogen, which is going to be the negative log of 0.090 molar, And we put that in our calculator, negative log 0.09. And I get 1 point, let's see, we have 2 sig figs, so 2 decimal places, 1.05 for our pH. So try that in your calculator, make sure you're getting the same answer. So we can see that we have a small concentration of HBr, so we're going to have a little bit higher pH, not super high, but 1.05. So that's how we can approach finding the pH of a strong acid. Now, if we want to find the pH of a strong base, then we have a little bit more to do, but not a crazy amount. So when we look at our dissociation reactions, we've got an example of sodium hydroxide, it breaks down to Na and OH. And I also have one of our group 2 metals, magnesium hydroxide. Now when it breaks down, we get magnesium 2+, and we get 2 hydroxide ions. So it's a 1-to-2 ratio. So your hydroxide is really what's going to control the acidity, or how acidic or basic our solution is. So when our ratio is 1-to-1, like the NaOH, so any of our group 1 metals, then we can approach this the same way, or very similar way, as our acids. So let's take a look at one of those. So if our concentration of NaOH equals our concentration of hydroxide, because it's a 1-to-1 ratio, if our solution is 0.7 molar NaOH, then we get 0.7 molar hydroxide. And this is where it is a little bit different. Since we have the concentration of OH, when we do the negative log, we're doing the negative log of OH. So we are calculating pOH. Okay, if you put in OH, you're finding pOH. If you put in hydrogen concentration, you're finding pH. All right, but that doesn't change the fact that we can still find our pH. So if I do the negative log of the hydroxide, OH, it'd be negative log of 0.7, and we get 0.15. Now, if we still want the pH, because that's our question, we can use this equation to help us. pH and pOH are always equal to 14. So 14 minus our 0.15, we can bring that in, and we get 13.85. All right, so that would be our pH. So we can see this is a very basic solution because we have a high pH. Very basic. Okay, so that's how we can do it if it's a single hydroxide. If it has more than one hydroxide, let's look at how we deal with that. So we're going to start, oh, I didn't do that. We're going to change this. All right. If we had, instead of NaOH, let's do our magnesium hydroxide. All right, so when this breaks down, we get that magnesium ion and 2 hydroxide ions. Okay, we get that ratio. So if our solution is 0.12 molar, or moles per liter, of magnesium hydroxide, we can just think about our ratio. We've got, for every 1 MgOH2, we form 2 hydroxide ions, right? We can do that mole ratio. So we get twice as much. So our concentration of hydroxide is 0.24 molar. So if we want to find our pH, we would find our pOH first, negative log of 0.24. If we calculate that, negative log 0.24, we get 2 decimals, so 2 decimals, 2 sig figs, 0.62 is our pOH. Our pH would then be 14 minus that value, 0.62. So 14 minus 0.62, we get 13.38. All right, so if we are doing one of our group 2 metals, metal hydroxides, then our ratio is 1-to-2, so we have to double our concentration and then find our pOH and then our pH. Okay, let's look at one more here. So it says, what is the pH of a solution that contains 0.43 grams of lithium hydroxide dissolved in 750 milliliters of water? What is the hydronium ion concentration in the solution? Okay, couple things we're going to do here. So first we want to find our molarity where we have grams of lithium hydroxide. So we have to first change those grams into moles, right? So our molar mass of lithium, grab my periodic table. Lithium has a mass of 6.94 plus a 16 for oxygen plus 1.01 for hydrogen. We get 23.95 grams per mole. So 0.43 divided by 23.95, and we have 0.018 moles of lithium hydroxide. Now we need a molarity. Molarity is moles divided by liters. We have 750 milliliters, which would be 0.750 liters. So 0.018 divided by 0.75, we get 0.024 molar lithium hydroxide. Now, it is a 1-to-1 ratio between this and just our hydroxide, so that equals our concentration of our OH minus. So our pOH would be negative log of 0.024. So negative log 0.024, and I get 1.62. So our pH would be 14 minus 1.62, and we get 12.38 as our pH. Now there's a second question here. So that's the pH. It asks for the hydronium, the H3O plus, or that's the same as the hydrogen ion concentration in the solution. So remember, this is in water, and that hydrogen and hydroxide form an equilibrium in water. So if we want our hydrogen ion concentration, then we need to undo our pH. So we're going to do 10 to the negative 12.38. So 10 to the negative 12.38, and we're going to get 2 sig figs. So 4.2 times 10 to the negative 13 molar. That is our concentration of the hydrogen ion. Since we have so much hydroxide, it's going to shift that equilibrium of our hydrogen and reduce it down. So that's how we can find pH, pOH for our bases. All right, we're going to work through some examples on calculating pH, pOH, hydrogen, and hydroxide ion concentrations for solutions. So our first column shows our concentration of our chemical. So whatever the chemical is on the left, that's going to be what we have in that first column. The second one is our concentration of hydronium. We can also think of that as our concentration of hydrogen. Remember, those are interchangeable, excuse me. We got our hydroxide ion concentration, and then pH and pOH. So our first one gives us our pH. So to relate it to our pOH, remember that 14 is equal to pH plus pOH. So if we subtract those two, we subtract 14 minus 9.6, our pH, we can get our pOH, which in this case would be 4.4. So from there, we want to find next our hydrogen and hydroxide ion concentrations. So starting with my pH, if I want to find my hydroxide or my hydrogen ion, so I'm going to label these. Column 1, 2, 3, 4, 5, 6. So I'm going to go from my pH in column 5 to my hydrogen ion in column 3. The way we do that is we're going to take 10 and raise it to the negative pH. So 10 to the negative 9.6 would give us 2.5 times 10 to the negative 10. We can do the same thing with pOH in column 6 and hydroxide in column 4. 10 to the negative 4.4 gives us our hydroxide ion concentration, which would be 3.98, so 4.0 actually, times 10 to the negative 5. And these would both be molarities because they're concentrations. Then for our final concentration here, we would find, to find our concentration of our solution, we want to look at what's in common here. So our hydroxide is part of our solution. There's one hydroxide in our solution when it breaks apart versus one of these chemicals. So it's a 1-to-1 ratio. So our hydroxide is going to equal our concentration of our whole solution. Again, this is a strong, all of these are strong acids or bases, so that hydroxide and the whole chemical solutions molarities will be equal. All right, let's take a look at our next one. This one is an acid because it's got that hydrogen in front. So the molarity of our hydrogen is going to be equal to the molarity of the whole solution. All right. Now to find our concentration of OH, there's a couple ways we can do that. One way we can find it if we just want to focus on what we already have. Remember that Kw, the equilibrium constant of water, is equal to our hydrogen ion concentration times our hydroxide, and that Kw itself is 1 times 10 to the negative 14th. So if we do 1 times 10 to the negative 14th and then divide it by our concentration of hydrogen on both sides, so Kw over our concentration of hydrogen will get our hydroxide. 1 times 10 to the negative 14th divided by 2.75 gives us 3.6 times 10 to the negative 15. Actually, we'd have one more decimal, so 3.64 times 10 to the negative 15. Again, molarity. Now, pH and pOH, we can do the negative log of the concentration of your chemical to find our pH. So negative log of 2.75 gives us, we get a negative, let's change my calculator. This is a very low pH, negative 0.439, so very acidic. And our pOH, we have negative log of 3.64 times 10 to the negative 15th. We get 14.43 or 404. All right. So definitely getting some different numbers there, above 14, below 0 in terms of our pH and pOH. That's telling us it's a really strong acid. Okay. Our next one, HI, we're given the hydroxide ion. So similar to the others, we want to find our hydrogen ion first. So we can do that Kw equation down here. So I'm going to do 1 times 10 to the negative 14th divided by my hydroxide ion, 2.79 times 10 to the negative 2. And we get 3.58 times 10 to the negative 13 molar. Okay, and again, this is another acid, so our concentration of our chemical is going to be equal to that hydrogen ion concentration. Oops, 1.3 molar. So those two are equal. We can again find our pH, so negative log of our hydrogen ion, 3.58 times 10 to the negative 13th, gives us 12. Did I do that right? Negative log of 3.58 times 10. Something is wrong here. Ooh, I missed a number on this. Okay, sorry about that. Let me edit. This is to the negative 3, not 13 over here. All right. So like, my pH is way too high. Okay, let's try that again. Negative log of 3.58 times 10 to the negative 3. And we get a pH of 2.45. So pretty acidic. Less acidic than our previous one, but definitely acidic. And then our pOH, we can do 14 minus 2.45, and we get 11.55 for our pOH. All right, last one, we've got a base. So we've got hydroxides, but this one has 2 of them. So if this is the concentration of our whole solution, the barium hydroxide, the hydroxide ion is going to be twice that amount. So 2 times 2.29 times 10 to the negative 3. So 2 times 2.29 times 10 to the negative 3 gives us 4.58 times 10 to the negative 3. We can use our Kw equation, 1 times 10 to the negative 14th, divided by that number. 4.58 times 10 to the negative 3 to get our hydrogen ion, 2.18 times 10 to the negative 12. Both of these are molarities. And then we can find our pH. So negative log of 2.18 times 10 to the negative 12. And we definitely get a basic solution, 11.66. 14 minus 11.66 to get our pOH 2.34. Whew. So I ran through a lot of those, but it's using the same equations over and over, okay? So if you get stuck or weren't sure about a particular part, just ask. All right, have a great day, guys.